Okay, let's quickly review what we were trying to do. Okay, we're trying to find out, you have a flexible plate onto which an incident wave is coming at particular frequency and wave number distribution. So it has a footprint on the plate as it comes in. Okay, and some of that will be radiated back, which is the reflected sound, and some will be transmitted to the other side. So to be more correct, and you don't have to worry about these, but these would be one in the most general form. Okay, two different media. But the important thing to do here is, number one, to write the pressure expressions for incident, reflected, and the key here is to get the directions right, to get the components right, and then a transmitted sound to the other side, and then the equation or expression for the plate displacement itself. Now, the important thing here is x. Kx must be the same in all of them. What is deriving this? Energy is coming from the incident wave. That's the driver, that's the force. And what we know, what the plate sees when that pressure comes is its footprint in the x direction, meaning lambda x, which becomes the wavelength, bending wavelength of the plate. That's all the plate sees. This wave that's now a bending wave that's traveling on it as a result of this incident wave. Plate doesn't know anything else. Because of that, it radiates out and it radiates to the other side, which is a transmitted sound. Now, let me remind you something, make it a little bit, not complicated, but something that you have to remember from last time. We said something about if the wavelength of the plate is smaller than the natural wavelength of the air corresponding to that frequency, it cannot radiate. We said that. Do you remember that? Yes. Well, we haven't said anything about this here so far. And we don't see any of that in this either. Do you know why? Why is that? It's not what? It's what? Reciprocity, reciprocal. In a way, yes. In a way, that's right. In the sense that just the way the geometry works out, that the sound excited wavelength can never be smaller than the sound wavelength. Just the way it is coming down, see? This at this angle or at any angle, this can never be smaller. But if you have a small one here, it cannot radiate. That's another story. But that shorter wavelength cannot be caused by a sound that's coming at it. Okay, this is an interesting and important factor to remember. Okay, so what that also means, well, here's something else though. Okay, here's something else. That is true with respect to this medium. Okay, but if you have a different medium on this side, that may not be true, because we're saying here the in effect, that's what we're saying, bending wavelength, bending wave speed is always larger than speed of sound, just the way it is exciting it. But that may not be the case here, because sound is coming from the other side. So there may be a case where the excited sound may not radiate to the other one because its bending wave speed is smaller than the speed of sound here. Does that make sense? No? Yes? Maybe? No? Is it complicated? No, okay, that's okay. Let's just talk about it, because this is almost like a puzzle. what we're saying is, as sound comes in, okay, its wavelength is always smaller than the wavelength of the plate. Okay? But is it possible that that may not be the case on the other side? See, this is... So I don't know how to draw it here, because you can't draw it if it's smaller, because there's no existing sound wave. Okay? So here, lambda b is always larger than lambda, and CB is large. But that may be a different story. We'll go back and explore that later. But mainly, I wanted you to remember and sort of put together what you have learned before about radiation condition, how wavelength must be larger than wavelength of the plate, must be longer than the wavelength in the air. Okay. Now, again, we have the expressions, we have the displacement for the plate, and the next thing we do is write the equation of motion for the plate. An equation of motion meaning velocity times its impedance is excited by the pressure on both sides. Positively, because it's from under pushing it up. Negatively, because the top is pushing it down. And from the top, it's incident and reflected waves together. What you said about use of the wave equation, we skipped. Yes, you do also use it in order to be able to find the relationship between them. But we have done it so many times, I'm just basically assume that we all know it. Now, that expression, we wrote it here. The next thing we do is use the boundary conditions. Okay, boundary condition relating the plate velocity to particle velocity above and below, so that we'll come back and use those expressions in the equation of motion and to come back and find out what the results are. Particle velocity above the plate, below the plate, and we have these expressions. We use a little small trick here to get this expression pi plus pr, okay? And then we also have a transmitted wave amplitude, all, if you notice, in terms of the amplitude of the plate vibration, and in this case also, of course, the known incident wave. Once we substitute all of those, we now have an expression for the amplitude of the plate vibrations. Now, depends on what you want to do. If you would like to get the expression for reflected pressure, transmitted pressure, we have all of these in terms of plate amplitude and the total impedance. So in this case, the transmitted pressure expression, we write it, and we have now this very nice compact form expression. And if what we can then do is, do you have any questions about this derivation? Clear? Okay. The expression for pressure transmission coefficient. sorry, that's it should not be a square, just amplitude. And of course the intensity. Intensity transmission coefficient would be then its square. Because these are plane waves, we're able to write this as a ratio, and that would give us if you want to have a complete expression for this, okay. This is just the same expression as before, but for example, this one, you can also write it as rho 2 C2 K2Z over K, or okay, same expressions. Going to give you a homework here, since you have been relaxing too much. I think this is homework number 4, okay? Derive the expression for sound power transmission coefficient for a plate. Okay. When it separates two different media. Now, this is the sound intensity coefficient when the plate is separating two different media. Okay, what would be different? Let's just talk about it for a second. What would be different for a sound power? How would you get the sound power transmission coefficient? What is that? Why is this a homework problem? Okay. Yes? But yes, you're getting to it. But this is intensity already. Okay, intensity has particle velocity multiplied for a plane wave. But there's something else. It's related to it. What is it that's going to give you a little headache when you solve this? If you go back into your notes later on, look at the same concept for refraction problems between two fluid media. Okay? You'll see that refraction angle is going to come into the play as an important factor here. If you include that, that will show up. So, and this is a textbook case you'll find in textbooks, but I'd like you to go through very careful derivation of that and understand it. Use figures, but make sure that you understand it, not the book. Okay, and so and derive this. In all of this, you always want to look at the equation. What is it telling me? Right? What is this one telling you? What are some of the things that it's whispering? Okay. Well, in all of these, it's a intensity transmission coefficient or pressure transmission. You want to know where it has a high peak value, where it is low. You know, where do you have problems? Okay, do you immediately see that this is not necessarily the maximum value, but it's close to it. Okay, because when this ratio is equal to 1, then this whole thing becomes 0. And in fact, when you look at it, that's the imaginary part. And then what will this do? If the imaginary reactive part of the impedance is 0, what does this mean? Okay, let me rephrase the question. If you look at these and assume everything is real here, okay? And this is an imaginary part. Imaginary part, if it is 0, what do you have left? Refraction problem, but from an impedance point of view, if you argue, okay, you have an impedance, you have the imaginary part and the real part. Okay, what do they represent? If this were 0, if you didn't have these, you have that, what does that represent? Take a look at it. What does it do? Does it remind you of something else? I'm sorry? Reactive power. It's reactive power. Yes, what does that mean? Mechanicals. What does it mean? Come on, we talked about this. This could be a good exam question, since you don't know. It'll be easy to grade if you don't, if you don't write anything down. Now, always what I do, you don't have to do this, but what I do is always go back to a single degree of freedom expression. An oscillator with a single degree of freedom, right? This is a very simple thing. And for electrical, you have a very similar, okay? And the impedance here, if you write the impedance, how would you write it? The equation of motion is, right? And if you do write these all in terms of, how do you do this? Oops. So you have an impedance of this shape, okay? This is, what am I? I'm not doing this right. I always go. Okay, hold on. Let's do this right, because it's important for you to relate these, and when you look at it, immediately understand what this means. Okay. And now we want to write this expression in terms of velocity. So, let's see. Is that correct? Okay. The impedance, the imaginary component and the real component. And the real part is, the resistive part is where energy is dissipated. Okay? If you don't have that, you only have the reactive part. And what does the reactive part correspond to? If it's zero, we call the resonant condition. Okay? Stiffness and inertia. So when you look at equations like this, when there's an impedance, you look at the imaginary part, the reactive part, and you look at the real part. Okay? Real part, we said energy is dissipated. How's the energy dissipated here? Exactly. Okay? Delta here describes the material damping of the plate. So some of the incident energy excites the plate. As a result, there's plate damping. Okay? Just like what I demonstrated earlier, which you didn't see. And what do these do? They radiate sound away. Okay? Some of it is reflected back, some of it is transmitted to the other side. So radiation of sound is a damping. In fact, in making calculations, radiation damping is a term. Okay? So you can call it radiation damping. We said in vacuum plate vibrations, but when there's radiation, we put the pressure back on it. That's taking energy away from the system. Okay? So this is the resonant, so-called resonant condition, and these are the dampers taking away energy from the system, from the plate. Do you see this now? Is it clearer to you? Okay? Now, just quickly, if this were not a couple of different things, we're still interrogating this equation. It has more stories to tell us. Okay? If instead of being a plate, this were a membrane, what would be different?
There will be no damping.
There will be no damping. Membranes can have damping in them, but go ahead. What else?
No stiffness.
Okay, so what would happen? Stiffness, where does the stiffness come in? The stiffness comes in through the bending, right? Bending vibration or bending modulus, so this would be 0. But then what do you have left with?
The inertia.
Exactly, the inertia. It just moves it as a flexible structure. Now, you still have radiation that goes to the other side, right? Because there's some reflection, some radiation. Now, so say again?
You still have damping.
Exactly. You still have radiation damping in this case. The other thing is, well, we said that because of the incident wave being real, this cosine theta 1 is always going to be real in this case. But should cosine theta 2 be imaginary? If it is imaginary, what does it do to the system? How does it react? If these numbers were imaginary, okay, then they again would be part of the reactive field. That means energy doesn't go away, okay? Energy, it's an exchange of energy with the fluid. You know, it vibrates, it pushes from here, okay, but the other side pushes it back. In fact, we really describe it as when you think about a plate vibrating like this, okay? In one cycle, it pushes the other up, down, as it moves up and down. So the fluid really just goes here. In the next cycle, it goes back. So, but if this were above that coincidence frequency, then it doesn't have time to go back and forth. It would just radiate outside. Physically, that's what happens. Okay, in one case, it's reactive, it just is around the structure. In the other case, the energy just radiates away. So these are, as long as they're real, they're damping. If they are not real, then they are part of the reactive field. Emrullah, you have a question. You look like you're puzzled about something.
I need to understand it when I look at the equation and when I saw the radiation part is imaginary.
Do I need to understand what?
When I look at the equation and when I saw the radiation part is imaginary.
When you look at this, an equation like this, an expression, of course you need to understand whether they're real, imaginary, because that will give you, see, when you take the absolute value, okay, that's going to give you the amplitude of transmitted intensity, okay? So physically, what we would normally do is look and see, you know, where the damping is, how much energy is lost, how much energy goes into this, and so on. So do you need to understand? Yes, I think so. Yeah. Yeah. Questions? No? Okay. Anybody else? All right. You should feel free to come and ask me questions after class or between classes, etc. Don't hesitate. There are only a handful of you, so I'm happy to answer any questions you might have. Yes?
Cosine is imaginary.
If, yes.
Represents the mass of the medium.
What does it represent? Well, what it says is it's a condition that represents no radiation. Okay, there's just no radiation moving out.
But it's then the kinetic energy of that
Plate.
in and out.
Exactly. In and out. Just moves back and forth. It doesn't, that disturbance doesn't travel away from the surface. Yeah, that's why we also call that condition a reactive field.
It's stored in
Exactly. It just stays there. Yeah. Okay. Okay. You have this as your homework. Let's take a look at this problem if both sides have the same fluid. It's a simple case. Okay. let's see, this is homework number 4. Okay, let's consider the case rho 1, C1, rho 2, C2, and of course cosine theta 1 is cosine theta 2, or theta 1 is equal to theta 2. In that case, please, yes, the equation of motion, or CB minus I omega A, remember now this is the radiation impedance, and plate vibration would be right, okay. This is plate vibration velocity, and the radiation field is expressed in the same form. Okay. Now, the transmission coefficient okay. You can see the expression simplifies, but if I write that out just a little bit one more time, and simplified. Okay. Right, one more expression following that, and then talk about it. Again, tau intensity, tau pi are, in this case, all the same expression. And if we simplify this, something is in. So right, that and I've changed some terms and I can't quite track it, but let's just write these and underline the sign to the fourth power theta just for a moment, okay? Now this is the inertia term, mass, stiffness, radiation loss, mechanical loss, meaning material damping. Right. Change the wave number someplace, and I'm not quite sure I remember, but in any case, the sound power expression, or sound power, sound intensity expressions are, oh, here it is, okay. Oh, okay. Okay. It's a mistake, that's why. K sine theta. Okay. Everybody's attention on me. We write it either kx sine 4 or just kx. Let me just put it down just for a second, please. K is it's just k sine theta. Okay, that's the when you compare it with this kx, just substituting that just to make sure that we have the angles involved in it. That's all. Okay. 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 This is, let's make some approximations. We talked about this so you understand basically what are some of the things that are involved in terms of the relative values. Let's make some approximations. Okay, what's coincidence? Coincidence is reactive term goes to 0. In this part, right? That goes to 0. And this affects, of course, the radiation at all frequencies, okay? So radiation, okay, coincidence affects radiation transmission at all frequencies in the range above the coincidence frequency, okay? Above the coincidence frequency, because this is a transmission problem. So let's take a look at the case where omega is below. What do we have here? I have k x over kb, which is the key number here. That's k sine theta over kb. And from before the last lecture, we had this expression. Okay, so let me come back here. So at low frequencies, such that we are below the coincidence frequency, or we are, omega is much less than omega c over sine theta squared, and omega c is critical frequency. And the damping terms are much less than mass term. What does all this mean? you look at this expression now, okay, we're now looking at, let's just remember what we're doing. We have a plate, and this plate could be this wall, right? We have a plate, we're looking at sound, you can hear the sounds coming, transmission to the other side. Well, there are high frequencies, low frequencies. So at this point, we're looking at what happens at low frequencies, okay, just for a moment. First of all, we are saying it is, everything is relative. When you say low, we don't give numbers, but with respect to. In this case, with respect to the coincidence frequency. And coincidence frequency is something that's determined by the thickness, properties of the plate with respect to the fluid medium, okay? So if this is a negligible term, okay? And also plate damping is negligible. We are left with this term, radiation term, and inertia term, okay? And if you simplify these, what we end up with is an approximate expression for sound power transmission at low frequencies. Because of the angle, we also say it's an angle-dependent transmission coefficient. Okay, now you can see what we're talking about here is at low frequencies, what is most important is the mass, not the stiffness, okay? Not the other properties. So it's a mass and also the angle at which the sound comes. Okay? Now, for omega m much larger than 2 rho c, well, rho c, for example, if this is some sort of a solid material, but sufficiently high frequency, but at the low frequency range. And if this number is larger than rho c, then we can write transmission loss expression as 20 log decibels. No, of course.
We drive this for intensity and power, but it's not equal to transmission coefficient. It must be square of the transmission coefficient.
Oh, it is, yes.
And consequently, this also is square.
This is square already. That's a square, but that's power transmission. So that's taken as a square. It's this, yeah. Yeah, thank you, yes. Okay. So this is also referred to as the mass law in some cases. Now we're, actually this is forming the basis for noise control studies, okay? And when you look at noise control studies, usually they will give you these equations, okay? This is the transmission loss expression, etc. But where it comes from is what we have just derived, okay? Now, let's distinguish between a couple of things. We said that's an angle-dependent quantity. This quickly here. Okay, so normal incidence mass law. Normal incidence meaning the sound is coming at the right angle. Let me just see for a second. Right. And the corresponding transmission loss would be 20 log mass and frequency. This is just a simplification. Okay. Sorry, theta is not 0, but normal incidence is theta 0. Yeah. Okay. There are a few other expressions that we can develop from these as special cases. But there are a couple of things that I just want to remind you in these. Let's see, do we have it here? Right, okay. The general expression, so sound power, then you can make a number of different approximations. You can look at the radiation loss, material damping, but the primary thing that we think about is whether there's a spatial resonance or if there are high frequencies, low frequencies, how some of these values change. These are engineering approximations. And this one particular case is when the frequency is low enough that this is negligible compared to inertia, and the material damping is also negligible. So you're left with the inertia of the plate and the radiation damping. And with those, we say for a thick wall, radiation coefficient is given by a very simple expression, but it depends on the angle of incidence. Okay. In fact, something to keep in mind is sound radiation at low frequencies is, how shall I say, mass dependent. In other words, if you want to prevent sound from transmitting from one side to the other of a wall or plate, etc., you increase its mass, nothing else. That's what it is. At high frequencies, of course, it's stiffness dependent. Just like a single degree of oscillator that I described a little earlier. Well, there's a lot more we can talk about plates, plate vibrations, but probably what we'll do is try to go back to them in terms of examples and maybe homework problems and such. But I need to stop it at this point, and then in the next section we'll start with the radiation problems and spherical coordinates. That should be interesting also. Okay, 2-minute break.